Section 3.1 is titled Numeration Systems. So the first thing to kind of talk about is, are you guys good? It's what we mean by the phrase numeration systems. So numeration system is a number system. Numeration is for number. And it's the way that we operate with our number system. So the first numeration system we're going to talk about is actually our own. You may or may not have known what it's called, but we have a system called the Hindu-Arabic numeration system. That's our system. It was developed by the Hindus, and it was transported to Europe by the Arabic. We have 10 digits. Our digits are the digits 0 through 9. Okay, so we don't have a digit 10. Digit means a single character. And we have a place value system that's based on powers of 10. That's the base of our number system. And we've already mentioned this before, but just remember that a to the power n like this means a times a times a times a, all that, n times. Okay? So what we're going to do next is we're going to explore some of the ancient numeration systems. So before anybody even has a chance to ask, no, you don't usually teach ancient numeration systems to elementary school kids. Part of this chapter is to give you some history about where we got to where we are and why we don't use some of the things that we don't use anymore. Part of this is also to give you some appreciation for what we do have and what you don't have to deal with. And then there will come a point in this lesson, and it'll happen next class period, where the point really is to make you feel a little bit uncomfortable with the way you would do math if you were in a different numeration system, so that you can appreciate how kids feel when they do math in our numeration system. Because it's really easy as you get further along to look back on your very early elementary school years and feel like, it's easy, why don't you get it? And so part of what we're doing in this particular chapter is actually getting ourselves in that mindset of, it's not easy when you see something for the first time. It can be very difficult. And so that's kind of the goal in this chapter, especially this section, okay? All right, so our first numeration system that we're going to look at is the Egyptian numeration system. These are the first pictures you get to draw. See, I told you, right? Some pictures there. These I actually did draw all of them, but that doesn't mean I drew them the first time the way I drew them. These are our Egyptian numerals. The first one is called a vertical staff, and the value of a vertical staff is 1. So you see a vertical staff, it has a value of 1. The second one is called a heel bone, kind of looks like the heel of your foot, okay? And it has a value of 10. The third one is called a scroll. Kind of looks like a number 9. It's a little bit more loopy when you see it drawn sometimes, where it looks more like this, you know, where it scrolls a little more around. And it has a value 100. The third one's called a lotus flower, and I've seen it drawn more than one way. The symbols that I've drawn in are the ones your book uses as the variations for this. But there are other resources that use them slightly differently or draw them slightly differently. This is how your book draws the lotus flower. I'm pretty sure you can guess at this point with the pattern analysis that we've been talking about in class. What do you think a lotus flower is worth? Yeah, it's worth 1,000. The next one's actually called a pointing finger, so imagine if it was like angled, right, or something, I don't know. Call it an angled finger or something, but they call it a pointing finger. How much do you suppose a pointing finger is worth? 10,000. I've heard the next one actually called 3 different things. Your book calls it a pollywog. I've heard it called a burbo fish. And I've also heard it called a whale. So this is supposed to look fish-like or tadpole-like, okay? It's got a smiley face on it and all that fun stuff and everything anyway, yeah? How much do you suppose a pollywog is worth, or its value is? Yep, 100,000. And then the last one is an astonished man. And I honestly think he's got to be astonished because he's worth $1 million. I mean, like, I would be astonished if I were worth $1 million, wouldn't you? That'd be pretty cool stuff. So he has a value of 1 million. I'm going to show you one other way that I've seen in a recent resource that I've used for drawing the astonished man, because I think it's kind of a fun one too. Looks like that. You see his feet? They're like curving, you know, or they're his legs. That's actually how one of the recent books are that we had drew him. So kind of want you to understand that, you know, just like in handwriting, in our handwriting, our 9s don't all look the same, our 4s don't all look the same. Like, how many of you make a 4 that looks like this, but some of you use 4s that look like that? We have some variations in how we write our symbols. The same would have been true in Egyptians, okay? So it's not just a one-size-fits-all. It has to absolutely look one certain way. Now, a few details about their system. What they did in their system is they repeated numerals to represent a value. So, for instance, if they wanted the number 300, they would draw 3 scrolls. And that's it. Their whole system was based on the idea of repeating the same symbol over and over again, okay, for whatever place value that they were working on. So, for example, this would be one digit or one number symbol, numeral in their system. We're going to do 3 things with most of our questions today. We're going to find the number that comes before, the number that comes after, and the value of the number we're working with. And they're kind of done in this order on purpose. I'd like to do the number that comes before, the number comes after first, because the idea is that you would be doing it kind of like an Egyptian would have, not by changing it into our system and then turning it back into theirs. You do that conversion thing kind of like that, and you're not really thinking like they would have thought in their system. Okay, so that's kind of the way that this is organized. So here's their symbol. I've got 3 scrolls and I've got a heel bone. And in our number system, we always look at the last digit when we're trying to go, you know, one number bigger or one number smaller, right? And you do the same thing in their system. That heel bone is worth what? It's worth 10, okay? So if you wanted to increase it by 1, what do you think you would have to do to sort of find the next number in their system? You'd add a vertical staff. So I know I just told you this is part B instead of part A, but it seemed to make more sense because it's the easier of it. The values at the beginning don't change, nor does this piece. But in order to do the next symbol, you simply add, not as in physically addition, but you simply include a vertical staff. That's increasing it by 1. Now, decreasing it by 1 on this particular one is the trickier one, because I don't want to, I mean, there's not a staff I can just take away on the end, right? That's what I would like to do. I'd like to just take a staff away. So what would I have to do you suppose, in order to sort of compensate for that? Yeah, if you took the heel bone and you break that heel bone up, I think I like that language, sort of breaking it down or breaking it into pieces, or maybe borrowing from it. That's the language we use in our system, right, is borrowing. So if you turn the heel bone into 10 staffs, could you take a staff away? Certainly. Now, that doesn't affect any of the scrolls, right? All the scrolls stay the same, but the heel bone's no longer there. Instead, we're going to have what? 9 staffs. And another thing that you'll see in their system sometimes too is, I guess we'll call it layering their numerals. So when they get too many of a numeral, they might actually write them on top of each other. Like they might write our 3 scrolls, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, like that. So you might see them layer them like that too. So there's not a right or a wrong to that. If you layer it, that's fine. If you write it all linearly, that's fine too. Either way, it's good. Okay, so now what we're going to do is we're going to use, when it refers to this value on all these part C's, it's referring to the value given, okay? What is the value given in the Hindu-Arabic numeration system? So we already established the heel bone's worth the value 10. So we've got a 10 on the end, if you will. What are the scrolls worth? 100, and how many of them are there? 3, so it's worth 300. So in essence, we have a 300 and we have a 10. That's a total of 310. And if you simply jumped to the 310 and didn't write down 300 plus 10, that's fine. But that's where it's coming from. It's piecewise that we're adding these things together. Okay, we're going to go the other direction now, all right? We're going to take one of our symbols, and we're going to write it in Egyptian. Okay, so we're going to be going both backwards and forward as we work through our numeration systems. So we have to take a look at each place value. This 2, what is the place value that the 2 is in our system? Like, what would we call that? The what's place? The 10,000s place. And what symbol in their system is worth 10,000? The pointing finger. So how are we going to represent the number 20,000? 2 pointing fingers. So draw yourself 2 pointing fingers. I promise I won't judge your artistic ability. Make it look like I can tell which symbol it means and we'll be okay. How about the 3? That's in the thousands place. What place, or what symbol did they use in the thousands place? The lotus flower. And so how many lotus flowers do we need? 3. The 1, what symbol is it in the location for? The 100 symbol, which is the scroll. How about the 4? That's the heel bone, right? The 4? So there's 4 heel bones, and then the 5? The staffs. 5 staffs. Okay, so let's talk about, we're going to do this on all of them. Benefits, drawbacks to this system. So what is a benefit to this system?
You can see how each part of it is like broken down and borrowing from the number.
Yeah, do you guys agree? You can see where the pieces come from and how they relate to our system really easily. There's a really natural kind of correspondence with our system. This idea of just repeating a digit to represent more of them is a pretty clean idea. Drawbacks. What would be a drawback to this system? Yeah, if you had, and it isn't, so what would make it be a big number in their system? Lots of higher numbers, I agree, like 8s and 9s and even maybe 7s, right? I mean, I don't want to draw the number 99,999, right? It's tedious. It's not real efficient. The system is not efficient. Okay, so efficient means quick to do, right? Effective means it's able to be done. This is effective. You can do it, but it's not very efficient. All right. The other issue, of course, is what happens if it's bigger than 1 million. We don't use those numbers every day, but there are times when what would you do? And they don't really have an answer for that. So there's not really a bigger than 1 million kind of number for them. All right, you ready to take a look at the Babylonians? Okay. Babylonians only have 2 symbols. They have what you probably would look at and call for me an upside down triangle, although it's just a triangle, okay? And we would call probably the second one something like an arrow or an arrowhead. Doesn't it kind of look like that? Now, when you draw these, literally, you do not have to shade them in for me. If you draw me an open triangle, I'm going to be okay with that. If you draw me an arrow that looks like a less than sign, I'm going to be okay with it. Okay, make sure that I can tell the difference between the two. I mean, don't make them look too much alike, but those are kind of our basic symbols. The value of the triangle is 1, and the value of the arrowhead is 10. And that's it. So you might be thinking, okay, what am I going to do to write like 90,000, like a whole bunch of these little, less than signs? And the answer is actually no. They actually had a place value system. See, the Babylonians were a little different than the Egyptians. The Egyptians didn't have a place value system. They didn't really need it. They just repeated symbols, and the symbols had bigger values, and so there was really not a place value system. But here they have a place value system. So what does that mean? Well, in our system, we only have 10 digits, right? But if I wrote down the number 9,000, the 9 would not be the value 9, right? The location where the 9 is tells you its value. It would be worth 9 thousands. correct? That's the same thing for their system. They have these different place values where the 10 in this place value is not worth 10. It's worth 10 times something else. So let's talk about their place value system, because it's not a value system that's place value like ours. We have a base 10 system. They have a base 60 system. So in our system, we have the ones place right here, right? And then we'd have the tens place, and then we'd have the hundreds place, and then we'd have the thousands place, and it goes up. And it goes up in powers of tens, like 1, 10, 10 squared, 10 cubed. Well, in a base 60 system, they have the ones place, and then they would have the 60s place, just like ours is ones and then tens. Our next one would be 10 squared. So what do you suppose theirs is? 60 squared. And then what do you think would happen? 60 cubed, and so on as you go up. Now the reality is that most of our numbers that we'll be dealing with will probably just have a couple of place values, okay, for their system. You might see one with 3 place values, but we're not going to go too far down this bunny trail. That's not the point, okay? But I do want you to see how their system works, because it's really different than the way we do our system, even though we have a place value system as well, and we have a base something else system as well. You might feel like we should have more in common, but remember, how many symbols do they have? 2, and we have 10, and that does make a difference. So let's take a look at their system. This would be a number in their system. And our goal first to find is the number that comes before, the number that comes after. Now, before we can even talk about that, you probably need to figure out where the place value breaks are, okay? So let's take a look at that. I'd like for you to notice that this right here has a value of 1, right? Because it's a triangle. These each have values of 10, and they're all sort of like grouped together. And then I've got these ones at the end. So you probably should write down a note to yourself that the 10s come before the 1s. So for example, if I wanted to write the number 11, I would write, I would write an arrow and then a triangle. That would be 11. I'd write the arrow first, triangle second. Arrow is worth 10, triangle is worth 1. So this is the number 11, okay? Arrows, triangles. So when I see arrows followed by triangles, this right here, after that vertical bar I just drew, is all one place value. So let's start out just by counting what you've got there. How many arrows do you have? 5. And how many triangles do you have? 9. And this is base 60, so is it okay to have a 59 in the place value? Yeah, because it's base 60. Kind of like ours is base 10, so we can have anything lower than a 10 in one place value. We can have a 9, we can have an 8. Base 60, this is 59. Okay? All right, so we'll finish more about like what this value is in a minute. The first question simply wants to know what would come before this. Well, just like when we were looking at the Egyptians, we looked at the end of the number and we took something away for what comes in, before it, right? So we can do that with this number too. What would we have to take away? A triangle, because a triangle is worth 1. So everything gets rewritten just like it is, except we take away 1 triangle at the end. So I have the triangle at the beginning, I have the 5 arrows, and then I have 8 triangles at the end. That would be the number that comes before. All right, so what are we going to do about the number that comes after? Well, again, right, like we would like to add in an extra 1. But what would happen if I added in an extra triangle? It would be 60, and I can't have a 60 in a single place value system because it's base 60. So you would add another triangle to the beginning. Okay, so there wouldn't be anything in the 1's place, but there would be 2 triangles in the 60's place. And we've already run into a problem. What problem have we run into? That looks just like a 2. So we don't have any way of distinguishing between 2 and between this symbol right here, which was supposed to be in the 60s place, right? So it'd be like a 120 is what this is. Each of these triangles in the 60s place are worth 60. That's a problem. And that's exactly what C's asking is, how else could the value that we just found in part B be interpreted? It could be interpreted as the number 2. Because they don't have any way to hold a place value. Now we have a place value holder. What do we call it? Huh? Not a decimal. 0. If we don't have any, any ones, we put a 0 in the ones place, right? They don't have a 0. That's a problem, obviously. That's a problem. Now, when it says this value, again, it's referring back to the original value. The original value that we had a triangle, 5 arrows, and then 9 triangles, right? And we talked about the fact that that was 2 place values. There was 1 triangle here, and you and I counted 59 in the second place value. So far, so good? This is the ones place, this is the 60s place. So think about what we do in our system. If you've literally had ones and tens and $100 bills, that's all you had. Okay, so don't work with the rest of our bills. It becomes more confusing because it's not truly a base 10 system. But if we had ones and we had tens and we had hundreds, and you told me that you had 603, you would mean you had 6 $100 bills, right? So this is like having 1 times 60, one $60 bill, if such a thing existed. Plus you would have 59 ones, 59 $1 bills. So 1 times 60 plus 59 would give me what? What was it? 119. And the original value I was given was 119. So the problem is that in their system, this numeral that we found in part A was basically 118. Not basically, it was. And in some weird way, this is sort of representing 120 or 2. And obviously, that's a problem. All right, so I'm going to show you now, because it's more difficult to do, how to go the other direction. How to take one of our numbers and turn it into one of their numbers. So we're going to take the number 43,205. And I'm going to teach you something that I call a division algorithm, okay? It looks kind of like a ladder. And we're going to keep using it throughout this section in every subsequent number system. Now, in this number system, we've already established that we have the ones place and then we have the 60s place. And the next one is 60 squared. But what is 60 squared? You're close.
Oh, 36.
3,600. And if we did 60 cubed, what would we get?
216,000.
Okay. Now, we only need values that don't get bigger than the 43,205 we were given, okay? So in ours right here, we don't need this one because it's bigger than the number we started with, okay? We only need the other 3. So that's the first thing you have to figure out is what numbers are you going to be using in the base system you're in. The numbers we're going to be using are 3,600, 60, and 1, okay? And what we're going to do is imagine that you came in and you had a whole bunch of crayons. In fact, you had 43,205 crayons. Aside from being in heaven, because that's a lot of crayons, and crayons are fun, and I don't care who you are, they're fun. Crayons are fun to play with, okay? You're going to group them into these piles. First of all, you're going to group as many of them as you can into piles that are worth 3,600. So 3,600 crayons in this pile, and 3,600 crayons in this pile, and 3,600 crayons in this pile. Okay? Eventually, you're not going to have 3,600 crayons left, and then you're going to group them into piles that are, of the ones that are left, into piles that are 60, and then at the very end, you're going to have some stragglers left over that go in the junk crayon drawer, okay? That's what you're doing. This is a grouping exercise. Well, grouping things into numbers like that is easiest if we don't physically do it, but we use division to do it. That's what we're going to do. So we're going to take our 43,205. And I'm going to show you how to draw this, okay? So you're going to do a division that looks like it's upside down. I didn't write it right. Like this. That's how I want to draw it. It's like, that doesn't look right. Not upside down. It looks like a top hat. Okay? So it's going to look like division on each side, a top hat. And what we're going to put on the left is we're going to put the biggest thing that's in our number system over here, 3,660 or 1, that works. The biggest number that we currently have is 3,600. And your calculator is going to be super valuable in this particular section. So if you have it, grab it. If you don't, just bear with somebody next to you and write down their numbers down. What I want you to do is I want you to take 43,205 and divide by 3,600. The question you're asking yourself is how many whole number times does it go in? There's probably going to be decimal stuff at the end. Ignore that for the moment. Just the whole number times is what we're looking at. For now, yeah. You can't on a test, though, so at some point I do want you to have your real calculators present so that you can use them. Yeah. All right, so how many times, whole number times, will 3,600 go into 43,205? 12. Okay, now I want you to use your calculator and I want you to multiply 12 times 3,600. Awesome. So that's almost perfect, right? Almost. So basically what we're saying right now is that we have 12 piles of 3,600 crayons. And we've got 5 left over. Now, for the purposes of what we're going to be doing later, what I want to do is do something that feels a little funny. We're subtracting here and we're going to have 5. We're going to write the next digit down, 60. Now, I know there's no groups of 60. And that's okay. We represent that with the number 0 over here, okay? There's 0 groups of 60. We're just using it as a place value holder. 0 groups of 60. Obviously, 0 times 60 is 0. And we still have 5 down here. And then our last place value is the place value of 1. And that's 5 times 1 is 5. So you're going to keep subtracting until you get 0 and you've divided by 1. So these are the last 2 steps that you will always get when you're doing this division algorithm. You're going to get a 1 on the left and you're going to get a 0 remainder. So here's the cool thing about this. The answer is right over here. I highlighted it in blue. It's a 12, a 0, and a 5. Now, that's the answer in our numbers, because 12, 0, and 5 are our numerals. It's not their numerals. So we still have to fix that part of it. But if you were thinking in terms of the place values over here, there's a 12 here, a 0 here, and a 5 here. Okay? 12, 0, and 5. So you ask yourself now, how do I write a 12 in their number system? An arrow, a triangle, and a triangle. That's how you write a 12 in their system, correct? In general, you would ask yourself next, the next digit, the 0. How would I write a 0 in their system? And the answer, unfortunately, in their system is, I can't. There's not a digit for that. So I just kind of move on past it because I don't have anything I can do about it. Now, in some of the other systems we have later, we will have zeros, and we will write the symbol for 0 right next, okay? And then we would need the symbol for 5. So what would the symbol for 5 look like in their system? 5 more triangles. Now, you could leave sort of a space, and sometimes you see spaces left for them, like that. So at the very least, you know, by leaving a space, you recognize that that means that these ones and these ones are in different place values. It still doesn't solve the issue of the 0, unfortunately, right? So in other words, this might actually mean that there are, oh, I didn't draw 5 yet, I'm sorry, 5 of these. It might mean that this is the 1's place and this is the 60's place when we know it's not supposed to be, right? It's supposed to be the ones place and the 60 squareds place, but we don't have a way to sort of show that there's a place value missing. There's just not an option for that. So obviously there's a problem here, right? Not having a 0 is a huge problem in their number system. But this is how you would draw it. I mean, like this is your final answer. That's how you would write it in their system. Unfortunately, it's just an ambiguous answer. I don't think you'd really want to be an accountant for the Babylonians. You would be setting yourself up for some problems, right? All right, Mayans. You know those Mayans that predicted the end of the world? That was supposed to happen 5 years ago, and we're still here.
There are some that was going to happen like
2012. Oh, yeah, I know, yeah. So we can pretty much guarantee it's not, right, Allison? Yeah, pretty much going to guarantee we're going to be here next week. All right, so there are 3 symbols in their system. There's a dot. There's a horizontal line. It's kind of short, but it's a horizontal line. And then there's the last one that looks something, it's supposed to look like a shell, like a seashell. It looks like bread to me sometimes too, yeah, and I've seen it look, again, drawn in different ways. This is the way your book draws it, so that's how it's drawn in here, but. Okay, the dot is worth 1. The line is worth 5. And the shell is worth 0. So already you should be like, well, that's good news. At least there's a 0. And it is good news. It solves some of the problems that the other systems have had, right? I have a 0. They do have a place value system, okay? So kind of like the Babylonians, they got the place value thing going on. It's not base 10. It's actually a modified base 20. So what do we mean by modified? Well, here's the deal. Well, I'll draw it here in a second, actually. It's written vertically as well, so the lowest place value is on the bottom and the highest place value is on the top. Okay, so they write it like a top to bottom. Big values on top, low values on bottom. And the dots go above the bars. So over here, remember that the big value went before the small value. Here, the small value goes on top of the big value. So let me give you an example of a small number. For instance, if you wanted to do the number 6, you'd do a dot with a bar underneath. Dots over bars. So this would be the number 6. Dots over bars. Okay, so let me talk about the modified base 20 system. All right, so first, you know what? First of all, let's just start here. Any idea why they might have used base 20? Any idea why we use base 10? These are related questions. Nope. We'll do ours first. Why do you think we use base 10? I usually say this before now. I don't know why I forgot to do so.
The metric system.
Huh?
The metric system.
Well, the metric system comes from the base 10, but not the other way around. So why did we choose 10? What's magical or special about 10? What? Okay, it is because it's even, but that's not still the why. No. Because we have 10 fingers. It's exactly why. It's because we have 10 fingers. So just imagine if God had made us without thumbs. It would be terrible, I agree. But we would use base 8. That's what we'd use. Because that's a part of our everyday way we think. We think in 10s because we have 10. So why do you think the Mayans thought in 20s? Fingers and toes, right? Like closed toe shoe kind of thing. That's not really like Mayan kind of stuff, right? All right, sandals, bare feet. Yes, okay. All right, so that's of value to us because it also shows what happens next a little bit. Why did they use this? What is this modified business? Well, we have a ones place value, right? Ones place. And then again, it's written vertically. These are place value lines. These are not their lines of like the number 5, okay? They're just holding spots for me. They have the ones place and then they have the 20s place, okay? So we had the ones place and then we have the 10s place. The next place value is not 20 squared. that would be a 20s based system. Their next place value is actually 18 times 20. Hang on. Multiply it for me. What's 18 times 20? 360. So tell me something that 360 sounds like to you. 360 degrees in a circle. Almost days in a year. And the almost days in the year is actually the issue for us. Yeah. So the Mayans were using it from a calendar perspective. You know them and their famous calendars, the world coming to the end, all the good stuff right there, right? Okay. 360 days, approximately 360 days in a year. Okay. So they really liked the 360 as a part of what was going on. So it's part of their number system. Now, to go up from here, though, they do start using powers on the 20. So then there's an 18 times 20 squared. And then you would do 18 times 20 cubed. And it would keep going from there. Again, we won't continue that process ever so high, but you could continue multiplying those out and you'd find their place values. Okay? So it's all base 20 except for that one weird 18 that shows up in sort of step 3 right here. Okay? And again, it's to get the number 360. That's why it's showing up. Okay, so dots on top of bars. Let's take a look at one of their number system or numbers in their system. I've got 2 dots in a bar, and then I've got 3 dots in a bar. Here's the first question people always get confused at when we get to the test on this. They get confused at where the place values change. Okay? Place values absolutely have to change when a line goes down to a dot, because dots always are on top of lines in a place value, okay? So if you see a line and then you see dots underneath them, that has to be a place value change. Just like over here with those Babylonians, when you see the triangle and then you see an arrow after it, the place value has to change. Okay? So dots, bars. So I see 2 dots and I see a bar above my purple line. How much value-wise would this be? Just practicing. Good. 7. How much value-wise is below my purple line? 9. Does everybody understand the 7 and the 9? Okay, this is not the number 79. Please don't think that's what I just wrote down. All I did was I counted within each place value what number is there. Okay, now let's go and look at the questions that are actually asked. Question number A. That's a number, right? A? Yeah, it's a number today. What Mayan numeral comes before this value? Okay, so with all of our number systems, we look at the last place value and we remove something to take it away, right? So what would I have to do to change the 7 with the dots and the lines and the 9 with the dots and the lines to get the number before it? Take a dot off the 9. You're exactly right. Okay, you take a dot away because a dot's worth 1, and you take it away from the lowest place value, which is the bottom part of their number system. So the 7 at the top stays, dot, dot, line, and I would end up with needing the number 8 down below, 3 dots and a line. That's the number before. Okay? All right, so if a dot's worth 1 and I take a dot away to decrease it by 1, what would I have to do to increase it by 1? I would add a dot, but if I added a dot to the 9, what would happen? I'd have 5 dots, and 5 dots equals a bar. So we would have still the dot, dot, bar from the 7, and then what would we have? 2 more bars. And do you see a problem? Yeah, you could leave some space to try to indicate that there's a break there. But it's not near as obvious as the breaking apart with the dot and the line that I drew the purple line at the beginning, right? Unless you're being extra careful and extra cautious, this looks an awful lot like what other number? This is actually question C, so 17, right? Each bar is worth 5, the dots are worth 2. This looks an awful lot like the number 17. And obviously that's, again, a problem. Let's use the original value again, right? This value means original value. The original value had a 7 and then it had a 9 in the place values. But these place values are worth what? What is the lowest denominator place value worth? It's the ones place. That always happens in every number system, by the way. And what's the second place value worth? 20, right? So we would take 7 times 20 plus 9 times 1 to turn it into our number. So what is 7 times 20 plus 9 times 1? 149. All right. You ready for the next one? Because we're going to go the other direction now. We're going to take our number and turn it into their number. Okay, so our number that we're starting with is 58,532. And we're going to do this division algorithm thing that I did over here again. But we're not going to do it with the numbers 1 and 60 and 3600 because those are Babylonian digits. Those are the Babylonian place value digits. We're going to do it with these values over here that I started writing out, didn't complete them, but the values in the Mayans. They have the ones place, they have the 20s place, they have the 360s place. What would come after 360? In other words, what would 18 times 20 times 20 be? 7,200. What would be the next one? 144,000. And for the purposes of our 58,000-ish number, that's too big, right? So I don't need to keep going. The one that we're going to do is going to need the 7,200, the 360, the 20, and the 1, because those are all the values that are smaller than the 58,000 we're starting with.
Could that have been like we would collect 144,000?
It could have been. There's nothing that I've read that indicates that, but I've thought that myself when I've seen it before, so I don't know the answer for sure to that question. Yeah. All right. We have 58,532. So the number you start with always goes under the top hat. 58,532. And you use the biggest place value that goes into that. And for us, that was 7,200. So how many times will 7,200 go into 58,532? 8. All right. And then what is 8 times 7,200?
7,600.
All right, 57,600, and then we're going to subtract. So 58,532 minus 57,600. Does anybody have it? You're close.
Oh,
932, yeah. Okay, we have to make sure we go down in place value. So what's the place value right underneath 7,200? 30, yeah, I keep saying it wrong too. 360. So how many times will 360 go into 932? 2. What is 2 times 360? 720. 932 minus 720. Okay, and our next place value down is the 20s place. How many 20s are there in 212? 10. That's going to give me 200, which leaves me with 12. Ones place is left, goes in 12 times, of course. And I get, do you see that 1 and that 0? That tells me I'm done. I'm dividing by 1 and I have a remainder of 0. Always it ends that way. And again, the answer is always over here. 8, 2, 10, 12. But that's the answer in our numerals. We need the answer in their numerals. So what is an 8? How do you draw an 8 in Mayan? 3 dots on top of a line, right? How do you draw a 2 in Mayan? 2 dots under the line we already had. Yep. How do you draw a 10 in Mayan?
A space and then 2 bars.
We hope we have a space But even so, we recognize that it may or may not be interpreted that way, right? Our best bet to do is to put a space. And then a 12. 2 dots and 2 bars, and we try to keep there not being a space, right?
What is the shell for?
The shell would be if we got a 0. I'm glad you asked, because I was going to mention that. Let's say, for instance, where I have the 2 right here, it says 0, because it didn't go in 0, it went in 0 times. Then when I'm writing that symbol down, I actually have a shell to be able to write in that place, instead of just being like on the last system where I don't have anything to write there. The shell actually solves the 0 problem, but it doesn't solve this sort of awkward making sure we've got the space business problem, which is still a little awkward on this one.